Welcome to lecture number 9. In today's lecture, we are focusing on dynamic scheduling in instruction pipeline, and specifically our target is to understand what is Thomas-Solo's algorithm. So, we will have a first quick recap on the concepts that we learned in the last lecture, wherein dynamic scheduling was introduced. This will help you to appreciate Thomas-Solo's algorithm in a better way. So, how basically dynamic scheduling works? This is what we have seen earlier. To allow out of order execution, what we do is we are splitting the ID stage into two. One is the issue stage, wherein decoding of instructions and checking for structural hazard happens. So, at the end of the issue stage, your functional unit is ready and you are being assigned to these functional units, and then while waiting for entering into the functional unit, the read operation is performed, where you wait until there is a data hazard. So, as long as issue is done, then you will reach the reservation station associated with the functional unit, and as and when the operand is available, you perform execution. So, in a dynamically scheduled pipeline, all instructions pass through issue stage in order. However, they can be stalled or bypass each other in the second stage, and thus entering execution in out of order fashion. And today our focus is on to understand Thomas-Solo's algorithm and what is the basis of dynamic scheduling. So, in Thomas-Solo's algorithm, you have your load and store buffers contain data as well as an address. So, your store buffers, this is the place where you store the address, and this is the place where we are going to store the corresponding data to be stored. So, for example, let us say I wanted to store a value 20 into the address, let us say hexadecimal 2000. So, this 2000 will be stored in the address portion and 20 will be stored in the data portion, and it is going to be a queue. As and when you are going to access memory using this address, we are going to work on it. Similarly, for loading, the value will be taken from memory. So, the byproduct of load will come only after from memory. So, we need only the address components. So, here also the number of entries as far as this memory unit is concerned can be considered as a reservation station. Now, in dynamic scheduling, we have basically issue. Issue is the very first stage. What we will do is get the next instruction from the FIFO queue, that is the instruction that you got after fetching. If the reservation station is available, issue the instruction to the reservation station if the operand value is there. If the operand value is not there, then we are going to wait in the reservation station. Now, coming to the execute stage, when all the operands are available, you store it in the reservation station and then you wait for it. When all operands are ready, you are going to execute. Loads and stores also use buffers, and no instruction will initiate execution until all branches that precede it in the program order have completed. So, we do not have a mechanism to address the control hazard at this point. And coming to write result, as mentioned, we are going to have a common data bus to which the output of all the functional unit is being connected. So, write the result into common data bus, thereby it reaches the reservation station, store buffer and the register file with the name of execution unit that generated the result. And for all the stores, they will wait until the address and the value are being properly received. Now, for the rest of Thomas-Solo's algorithm, we will first try to see how the functional unit looks like. So, this slide will help you to understand Thomas-Solo's algorithm in a better abstraction. You have an instruction fetch unit from where instructions are being brought and that has been kept in memory, and you have a unit called register status indicator. The purpose of the register status indicator is to mention about what is the status of a register value. For example, at this particular point, the content of register, whether it is really available in the register file or whether it will be produced by some execution unit. And then we have various execution units, and as mentioned, all execution units are connected to a common data bus, and the input side of execution unit, we are having the reservation stations, which are basically queue to enter into these execution units. Now, instructions are fetched one by one and decoded to find the type of operation and the source of operands. We have the register status indicator that indicates whether the latest value of a register is in the register file or currently being computed by some execution unit. If so, it states the execution unit number. So, if the register status indicator of a register, let us say R5, if that value equal to 0 means go to the register file R5, that will contain the latest value of registers. If this value is any number, let us say I, which is not 0, the meaning is at this particular point the latest value of the register R5 is not available in the register file, rather it will be a value that is going to be produced by a functional unit whose number is I. So, register status indicator is a very important component or a facilitator which will produce you the latest value associated with a variable. If RSI is equal to 0, means your value is up to date, go to the register file, take the value, and that is the latest one. If the RSI value is not equal to 0, then it is actually mentioning a functional unit number. If RSI value is equal to 10, 10th functional unit will produce a value and that is to be written into this register. So, there is no point in going into register and taking the value. Whatever be the value that is produced by the 10th functional unit, take it and use. So, it is actually a reflection of what is the latest value associated with a register. Now, if all operands are available, then operation proceeds in the allotted execution unit. So, this is the place where you generally wait. So, you have your operation details and the operands are available there. If operands are available, then it is ready for execution. As and when the execution unit is free, you are going to enter. If operands are not available, the only possible way by which you get the operand is through the common data bus that is been connected. And once the data is ready, you are going to update your reservation station, thereby entering into execution. Now, how will you get these values? You can see that all execution units are connected to the common data bus. So, when we can say that the operand is not ready? When the value is still under process in some of the functional units. So, as and when this functional unit completes, the value is written into the common data bus and then it is going to update your reservation stations. So, if all operands are available, then operation proceeds in the allotted execution unit, else it waits in the reservation station of the allotted execution unit, pinging the value of the CDB. Every execution units write the result along with the unit number onto CDB, which is forwarded to all reservation stations, register file and memory. Now, the concept that we have to understand is you have a common data bus to which many execution units are being directly connected. Now, if somebody watches here, let us say a value X is available in this CDB. The execution units which are waiting for some value, how will they know that this X is produced by which functional unit? So, in this case, whenever a functional unit produces a value, it has to mention the functional unit name also, that is very important. If the functional unit name is not mentioned, then the reservation station entries may not be able to distinguish between which functional unit produced this value. Now, let us take a simple example to understand how these register status indicator values are being operated on. Consider a scenario where you have a program to execute. The program is already given, there are 6 instructions in the program. Now, you have 10 registers from R1 to R10 and register status indicator is already shown here. So, this is the RSI value of these 10 registers. This box will tell you what is the current instruction that we are operating on, and we have total 6 functional units. These are the 6 functional units and these functional units are going to operate on. Now, for the time being, let us assume all these functional units, all these 6 functional units are identical. So, whatever be the operation, it can be assigned to any functional unit. Now, see what is the meaning of register status indicator. At this point, the RSI value, RSI stands for register status indicator, of all the 10 registers are 0. If RSI value is equal to 0, the meaning is for all these registers, the updated value is available in the register file itself. So, go and fetch from the register file, that is your operand. Having said this, let us move into the example. So consider the first instruction, add R1, R2, R3. All instructions are of the format. The first operand is going to be the destination. So R2 and R3 are being added and you are going to write the result into R1. Now in this case you have to see that what is the value of R2? The value of R2 was 0. What is the value of R3? R3 also is 0. That means both the operand values are available inside the register file. So go to register file, take the value of R2 and R3 and you are waiting in the reservation station of functional unit 1. Now in the functional unit 1, you can see that since both the operands R2 and R3 value are already available, it will start execution, its instruction. At this point, the R1 value is to be updated by functional unit 1. That is why RSI value of R1 equal to 1. So if anybody who wants the value of R1, they should not go to register file. They should look into the value that is produced by execution unit number 1. This 1 indicates it is the name of the functional unit that will produce a value to be updated to R1. So that is the role of this. So with this, our first instruction is over. The change that is going to happen, since the source operand of the instruction R2 and R3, RSI value is equal to 0, operands are available, perform the operation in the execution unit 1 and update RSI value equal to 1, because 1 will produce the value to be returned to R1. Moving on to the next instruction, here I am going to perform a store where the source operand is R1. So the content of R1 has to be returned to a memory location whose address is computed by R4 and 50. Now we have to see that at this point value of R1 is not available. So this instruction will be forwarded to the second functional unit, wherein you are in the waiting stage and you are waiting for the result that is produced by 1, because at this point RSI value of 1, R1, which is the operand, is 1, meaning my value is not available, it will be produced by some other functional unit. So it is the name of that functional unit that is being written over here. So second instruction cannot execute, it is waiting for a result produced by the first functional unit. Now let us try to see what is the third instruction. If you look at the third instruction, it is R5 and R6, these are the two operands. These operands, if you look at the RSI value, the operands are available. I can perform the operation and I will write the result into R1. So looking at the third instruction, R5, R6 are the source operands and RSI value tells that RSI equal to 0. That means you can go into the register file, get the data. Since operands are available, I will assign them into the third execution unit. So the third execution unit will perform, this is the third execution unit, your I3, this is I3 is the third instruction, it is going to execute. Now at this point the result is to be returned to R1. So R1 RSI value is made to 3. So anybody who is going to look for value of R1 after this point, they should not go to register file, they should not wait for a value which has been produced by the first execution unit, it should only look for the value that is produced by the third execution unit. Now moving on to the fourth instruction, here R1 is your source operand. You can see that the RSI value of R1 is 3. The RSI value of R1 equal to 3 means R1 value is not readily available. You have to wait for the result produced by the third execution unit. So upon completion of this execution unit only you will get R1. Now coming to R8, R8 RSI value equal to 0, and so one of the operand is available, the second operand I have to wait. That is the reason that the fourth instruction is in the waiting stage in the fourth functional unit, waiting for a result that is produced by the third functional unit, and the result is to be returned to R7. So from this point RSI value of R7 is equal to 4, because the result that is produced by the fourth functional unit will go to R7. So anybody wanted the value of R7 from this point, it has to wait in the result from the fourth functional unit. Moving further, we are now going to perform a store operation on R1. When you perform a store operation of R1, we know that the R1 RSI value is 3. So you cannot proceed. So it is going to wait for a result that is produced by the third functional unit, and R4 is available because RSI value of R4 is 0. So, one of the operand is available, you compute the address, but then you cannot perform the operation until the third unit produces the result. Now, if you see, there is one instruction which is waiting for a result produced by the third functional unit. Similarly, there is another instruction also that is going to wait for a result that is produced by the third functional unit. So, there is a dependency between the third instruction to the fourth and to the fifth. Now, both are waiting together. Now, if you see, the moment third will produce a result, both instruction 4 got its data and instruction 5 got its data, both will execute parallelly in two of the functional units. Let us now move into the last instruction. Last instruction is add R1, R9 and R10. So, here if you see, after this instruction R1's RSI value will become 6, and since it is R9 and R10, you are going to have your sixth instruction executing directly. So, you have your third instruction executing, you have your first instruction executing, and you have your sixth instruction executing. The peculiarity of this is, in all these three instructions I1, I3 and I6, the operands are available. Since operands are available, it is not waiting for anything else. As long as when you get functional unit, you start executing. Whereas your second, fourth and fifth instruction are waiting. Second is waiting for a value of R1. So, second is waiting for R1. Fourth and fifth also is waiting for R1, but they are waiting for different versions of R1. I2 wait for I1 and I4 and I5 wait for I3. So, effectively 3 instructions are executing and others are waiting for appropriate result. So, if you look at the whole program can be converted like this. You have your result to be produced in R1. Now, that result which will be produced by unit number 1 is going to be used. Here also you are going to produce a result to R1, but unit number 3 is whatever is the result produced by unit number 3 act as an operand for fourth instruction as well as the fifth instruction. So, operand forwarding has automatically happened. So, what happens is this is operand forwarding, this is also operand forwarding. You are going to forward the result through some functional unit, and register renaming also happened. So, if you look at, you can see that there is an R1 where I am going to write the result, there is a wiring to write the result, there is going to write the result. So, all are going to write to different time to the same register R1, but this wow hazard is not happening because instruction those who want one version of R1. So, only instruction 2 want this R1. So, to 2 I am not telling you should go to R1, you are telling the functional unit. Whereas 4 and 5 want this result of R1, they are not given directly access to R1, rather they are being asked to read the value that is been produced by U3, and after instruction 6 they will look into the result produced by the sixth functional unit. So, if you look into the example that is been discussed right now, it is very simple. You have a sequence of instruction, you take an instruction, see what is the operation to be done. If the functional unit is free, you are going to assign them into the appropriate reservation station. If the operand is there, so how will you know whether operand is there? Look at register status indicator. If the value is 0, go and fetch the operand value from the register file and keep the operands ready and wait in the reservation station associated with the functional unit. If the operand is not available, which you will come to know by looking at RSI value, so you are waiting in the reservation station pinging the common data bus. So, as and when the appropriate functional unit produces a result, the reservation station which are continuously pinging the CDB will grab the result, get the operand and then start executing. So, reservation station and register status indicator are playing a very crucial role in handling operand forwarding, in handling register renaming associated with the instruction pipeline. Now, the execution unit 6 on completion will make R1 entry in the register status indicator 0. So, as and when the sixth instruction completes the operation, it writes into R1 and then make RSI value equal to 0. Similarly, unit 4 will make the R7 entry equal to 0. So, this is how the whole structure looks like. We have had a discussion, we have reservation station, this is the reservation station for adders, you have reservation station for multipliers. So, every functional unit has its own reservation station, and this Q is acting as a reservation station for memory unit for load and store. We call it as load buffer and store buffer, and CDB updates is floating point registers or whatever is your register file, and at the same time CDB is connected to the input of the reservation stations also. So, now let us see what is the content of a reservation station. Each reservation station has 7 fields. We represent it as operation, Qj and Qk, that is one couple, Vj and Vk, that is another couple, A for address field, and there is a busy field. Now, the op tells what is the operation to be performed on two source operand S1 and S2. So, if the operation is going to be S1 op S2, the op field will tell you what is the operation. Let us say it is an add operation, logical shift operation, like that. Now, the second and third field is Qj and Qk. If the operand value is not available in the register, because your register status indicator is reflecting like that, then you will get the operand from the output of some functional unit. So, Qj and Qk indicates the functional unit that will produce the result. The reservation station that will produce the corresponding source operand. A value of 0 indicates that the source operand is already available in Vj or Vk. So, this Qj and Vj are coupled, Qk and Vk are coupled. If value of Qj equal to 0, that means Vj is your operand. If value of Qk equal to 0, then Vk is the operand. So, Vj and Vk are populated from taking the value directly from the register file. If Qj and Qk contains a non-zero value, then Vj and Vk is not at all used, because Qj and Qk will tell you the functional units that will produce the result. So, Vj, Vk is the value of the source operand taken from the register file. Only one of V field or Q field is valid for each operand. So, if Qj is valid, then Vj is not valid. Similarly, if Qk is valid, then Vk is not valid, and vice versa. And for loads, Vk field is used to hold the offset field. Now, coming to A is used to hold information for memory address calculation for a load or a store. So, initially the immediate field of instruction is stored here, and after the address calculation, the effective address is stored in this field, and busy indicates that this reservation station and its accompanying functional unit are currently occupied. So, the register file has a field known as Qi, that is known as RSI. So, Qi is the number of the reservation station that contains the operation whose result should be stored into this register. If the value of Qi equal to 0, no currently active instruction is computing a result destined for this register, meaning that the value is simply the register content. So, if Qi equal to 0, then Ri value is available in register file. If Qi is equal to n, then Ri value will be updated by functional unit number n. So, we understood the concept of how Tomasulo's algorithm works with the help of an example. Now, to get a better clarity, a set of instructions is being given, and from these instructions, we will try to see how the reservation station values are being updated. So, consider the instruction that is given in the slide, two load instructions. Let us say we have a multiplication instruction, then sub, then div and add, and you can see this F indicates the name of the registers and R indicates name of integer registers. So, let us look into a scenario where I have two load store unit, load 1 and load 2, two adders, add 1 and add 2, which can perform addition as well as subtraction. So, we have 3 adders which can perform adding and subtraction operation, and we have 2 multipliers which are capable of performing multiplication operation. So, we have seen that in the reservation station associated with them, we have an operand field, you have a Vj, Vk field. If the value is there in Vj and Vk, that means they are the real operands. If Qj and Qk value has been filled, then they are the values of the functional unit which will produce the result, and A will produce the address. So, first is a load instruction. So, 32 plus R2, 32 plus the register content of R2, that is there in the address, and then once you do this instruction, the result has to be stored into F6. So, this is the register status indicator that you see on the bottom. So, we are using 5 registers F0, F2, F4, F6, F8. Sorry, we are using 6 registers F0, F2, F4, F6, F8 and F10. So, this indicates that at this point the value of F6 will be produced by the load 1 unit. Load 1 is nothing but the name of this load unit. Now, we move to the second instruction. So, when you move to second instruction, you can see that that is going to write the result to F2. So, after this point, F2 RSI value should contain load 2, the name of the functional unit that will produce, and it is basically 44 plus register content of R3. So, that is there in the A field. So, for loads, this Vj, Vk, Qj, Qk fields are not used at this point. Now, we are going to the multiplication instruction. You know that one of the operand of multiplication instruction is F2, the first operand. The second operand is F4. If you look at F2, the value of F2 will be produced by load 2, whereas value of F4 is 0. So, the first operand F2 is not available because RSI indicates that load 2 will produce the result. So, Qj value will contain load 2, meaning to get the value of F2, you have to wait until load 2 produces a result. Whereas, F4 is an operand that is available. So, you go to register file, the content of the register file is the value of Vk. So, Vj is blank. So, at that time Qj, so these two are coupled together. So, if Qj is non-zero, do not look into the value of Vj. So, here if Qk is 0, then I have to look into the value of Vk. So, this is basically you have a value 0 here. So, first operand is not available. So, I wait for the result produced by load 2. Second operand is available, that is why the value is kept in Vk field. So, after this load operation, your result is going to be returned to F0. That is why from this point onwards, the RSI value of F0 indicates mult1. So, anybody who wanted a value F0 from this point onwards, they have to look into the output produced by mult1. Do not go to the register file to access F0. So, if you access F0 from the register file at this point, it is a wrong value. You should not use it. The latest value will be produced by mult1. Moving further, now we are moving into the subtraction operation. So, I can make use of my adder number 1. Let us see what are the operands. F2 is one operand, F6 is another operand. F2 RSI status tells that load 2 will give you the latest value, and F6 RSI value tells that load 1 will give you the latest value. So, this is a case wherein both operands are not available. So, you have to wait. So, in that case Qj will produce first and Qk will produce the second value. Now, after the subtraction instruction, the result will be returned to F8. That is why F8 RSI value is given to adder number 1. So, adder number 1 will produce a result to F8. Now, we move to the division operation, which is being carried out in mult2 functional unit. Look at the operands. The operand is F0 and F6. F6, you know that load unit is going to produce the result, whereas F0, it is a multiplier that is going to produce the result. So, in this case also both Qj and Qk are being filled up with non-zero values, means both the operands I have to wait for the output produced by the functional unit. So, the moment F0 and F6 generates the values, then this reservation entry has the full operand ready and it will move into the functional unit. And now we come to the last instruction, that is the add instruction, where you can see first operand is F8, second operand is F2. F8 knows that it is result of add 1, and F2 you have to wait for the result of load 2. So, this is the way how all these instructions are going to work. Now let us look into the reservation station, and we can find that the load instruction, which is the very first instruction, the address is ready. So as and when you are able to access the memory unit, it will produce the result. So based upon that, the load 1 and load 2 will produce some result. The moment load 1 produces a result, this operand will be available to the reservation station of adder number 1 and to the reservation station of multiplier number 2. So both of them are actually waiting for an output produced by load 1. So the moment my load 1, the first load unit produces the result, these two reservation station which are waiting for load 1 will get their operands. The moment load 2 completes, then this field is available, this field is available, and this field. So there are basically 3 instructions that will wait for the value that is produced by load 2. Now if you look at this, when load 1 and load 2 both completes, then this subtraction operation can proceed because both of its operands are now available. So the reservation station of this add 1 unit, wherein the subtraction is waiting, they are continuously pinging CDB. The moment a value is produced by load 1, it takes that value. Similarly, the moment a value is produced by load 2, it takes the value. Once you get both the value, it starts executing. Similarly, once it completes, then this is ready and this add also can continue further. Similarly, the moment multiplication operation is completed, how can multiplication complete? When load 2 completes, that will take one of the data, the second data is already available, multiplier 1 will produce a result, and when multiplier 1 will produce a result, this multiplier 2 is going to make use of that. So it is actually a cascading effect. So the whole dependency waiting for one data from other. Dependency relations, any instruction that is waiting for any other instruction where there is a data dependency, it is easily resolved. In this way, operand forwarding, register renaming, handling of var and wow hazards, everything is taken care of in the Tomasulo's algorithm. So with this we come to the end of today's lecture. Just a quick recap of what are the concepts that we learned today. We understood what is dynamic scheduling, where you have issue is done in order and issuing is to the reservation station. If there is no reservation station available, then issue will not work. Now once issue is over, then execution can be out of order depending on the availability of operands. While we issue instruction into the reservation station, if operands are available from the register file, take the value and keep the operand along with the instruction waiting in the reservation station. If the operand is not available, you are waiting for some other previously executing instruction to complete, then that execution unit number is mentioned. So the CDB where the output of functional units are being written, it is connected to all the reservation stations. So as and when the CDB update happens, reservation station also get the updated value. In this way, Tomasulo algorithm gives you a platform by which dynamic scheduling is being done. To get a deeper understanding about this topic, I request all the students to kindly refer the textbook Hennessy and Patterson and read it through multiple times, and if there is any doubt, feel free to ping us in the online forum. Thank you.